C-C bonds, or this peak corresponds to C-N bonds. But when we compared the UV vis of aniline and benzene, we didn't say that, oh, benzene has only CH bonds in it, so it's got a lambda max of 178, whereas aniline's got a CN bond in it, and it's got a lambda max of 220. We didn't fingerprint things using UV vis. UV vis was based mostly on polarizability and energy of electronic transitions, right? So what's more polarizable, aniline or benzene? Aniline is more polarizable, right? More electrons. It's got lone electron. It's got a lone pair on the nitrogen. And so what had the higher lambda max, or the longer wavelength lambda max? Aniline or benzene? Aniline, right? Aniline had a lambda max of 220. I'm grading your homework now, so I know the values off the top of my head. And so longer wavelength equals lower energy, and longer wavelength is lower energy. So if aniline is more polarizable and it absorbs that longer wavelength, it takes less energy to make this electronic transition in aniline and more energy to cause an electronic transition in benzene, because benzene is less polarizable. So those electrons don't want to move, they're held more tightly, so we need to pump in more energy or a shorter wavelength to cause an electronic transition in benzene. Now that's a very subtle point on the homework. The take-home message here is that FTIR gives fingerprints of chemical bonds and UV vis doesn't. But also knowing the difference between these transitions, where we have electronic transitions in UV vis and bonds, vibrational bonds in FTIR. That's very important, and a lot of people goof that up on the homework, so we'll cover it tomorrow if I remember. Does that clear up the difference a little bit between UV vis and FTIR? Yeah?
What do we have to know about IRAS or how much increase?
Well, so IRATS is just, intensity is reflection, absorption, transmission, and scattering. And so you had some homework problems on absorption and transmission, right? So those would be good things to remember.
So now, you don't need to know it in too much detail.
Well, there's a lot of detail around transmission and absorption, right? There's formulas that go with those. We know that 20% transmission does not equal 80% absorbance. We know units on absorbance, things like that. So, those would be good things to know. Yeah.
Can we get back to lecture number 2?
Get back to what?
Second lecture. With that chart with that.
Oh, sure. Let's put it up just so we can remember. You want to ask a question about it?
Yeah.
Okay, go ahead.
We have the second part. There's a relationship between these similar molecules, and for the induced van der Waals forces.
Wait, where's the chart?
Yeah.
It's in lecture.
The chart that just like question.
Oh, do you mean this chart?
No.
Which chart do you mean? Show it to me.
That has this part here. Plus that big chart that shows like
Oh.
van der Waals forces.
Oh, yeah. Okay. This chart.
Yeah. Here for H2O and CH4 at the bottom, it's 9 for the van der Waals forces. Yeah, here it's 9. And if we try to find that, I tried to plug in the numbers, but I didn't get 9. And then I got only 5.
So when we look at dissimilar molecules, and we look at the induced forces for water and methane, you're looking at this one, right?
Yeah.
So So you tried to plug in the dipole and the polarizability and all that stuff?
Yeah, because here like the dipole moment for CH4 is 0. So that will give us 5 minus. The dipole moment for CH4.
Come on up here and point to what you mean. Watch the card, yeah.
It's here for CH4, the dipole moment here is 0.
Yeah?
And we need this number to find the number here, right? Because here it's multiplied by 2. So this is 5. That will give us 5 here. So from where it becomes 9. We just couldn't find like the relationship if it's there's something wrong here.
No, so this table, I understand what you mean, thank you, yeah. So, I think that this has to be taken at a given radius, right? I think because all of these are at a given separation, where is it? Because all of these interaction energies, right, whether we have orientational, dispersion, or induced Debye, they all have a term in terms of radius. I think, I've never plugged these values in myself, so I don't know if something's wrong. But these tables, well, I'm not sure. I'm not sure if you could plug in these numbers here and get exactly, you said you got 5 for this?
Actually, I didn't do the calculations, but here it's multiplied by 2. Like for the H2O, that's why we get 10. But like at the bottom, no, it's like the 2 separate like calculations. So if this one is 10, then this one should be 5 because the dipole moment for CH4 is 0. So
yeah, I think though when you, I know what you're getting at.
Because I can follow actually the trend here when I compare H2O with CH4 with the HCO with HI. Just like there's no.
Well, so here the induced, so this is CH4, right? And the induced is 0 here.
Yeah.
And with neon CH4, it's 0 here, right? And then you have iodide. So this is this CH4 right here?
Yeah.
So you have water, and so the induced interaction, because you have a dipole here for water, so the induced interaction is going to be something, right?
Yeah. Mine is not too much. If you compare like Na with CH4 with H2O and CH4, it doesn't make sense.
Well, so why don't you bring the calculation tomorrow to class, or we can look at the calculation. I think what I want to stress on this table is the relation of the magnitude of these forces to the different molecules. Whether you can calculate these quantities directly from what's given is not as important to me.
Like the induced, the first comment. Is it like respond to the polar with one polar or two non-polars?
Yeah, so the induced interaction has to do with the polarizability, right?
Yeah.
Induced interactions are all, because this alpha 0, let's see. Well, let me go back to my, so high induced interaction, so here's the induced, right? So alpha is related to the energy of the induced interaction, and so the induced is going to be due to the polarizability, whereas your orientational interactions are due to the strength of the dipole, and the dispersion forces are due to the size of the thing, right? So any induced interactions is going to have to do with the polarizability.
So what molecules should be
Hold it down, please, you guys, so I can hear what's going on. Thanks.
So what molecules should be like polar to in order to have like orientational forces?
So for orientational interactions, you have to have polar molecules, right? Because you have to have something that has dipoles in it. And so if we look at the equation for orientational, right here, you need to have two dipoles interacting with one another to have orientational forces. So anything that's got dipole in it, right? HCl and HI have orientational because they're both dipoles. However, neon and methane don't have any orientational because there's no dipoles there, right? So you have to have two dipoles to get orientational.
What about the induced? Like at least one of them should be polar, right?
One of them should be what?
Polar.
Yeah, for orient. Well, both of them have to be polar for.
Induced forces here, attraction.
Let's see, for induced. It looks like it. I mean, there could be induced interactions for methane, right? You can still have induced, but it turns out that they're very small for methane because methane isn't very polarizable. But if you have, say, potassium and potassium interacting, you know, remember what the induced is. If you bring these two things close enough, right, and you have some electron density here causing some induced dipole over here, right, you're going to have an instantaneous dipole in each of these. So if the electrons are big enough, or if the polarizability is high enough, you can have induced interaction. So the induced interaction on this van der Waals energy is only due to the polarizability. It looks like there you have to have some kind of dipole too. Mm-hmm. Yeah?
Can you have induced interactions with a polar and a nonpolar molecule?
Sure. So you can have induced interactions, you know, if we look here, let's see, polar, nonpolar, which one has induced? So water interacting with neon, right, has an induced interaction. It's pretty small, but you can have an induced interaction between a polar and a nonpolar. So I think, let's see, water methane, well, it looks like water methane has even a higher induced interaction. So based on this, when we compare water methane interaction versus water neon interaction, which is more polarizable, neon or methane? What's got the higher induced interaction? Methane's more polarizable, right? It's more electrons, bigger, all of that stuff. Yeah?
What are the main things we have to learn about that thing?
Oh, we've talked about it for 2 days, right? So the main things are, where do these different interactions come from? So what's the physical situation when you bring HI